Hello and welcome to our third video on basics of acid and base equilibrium. What we're going to talk about today is determining the pH of salt systems. The joke is how to really manage your pool. So let's start on. So when we look at a salt, an ionic compound, back when we learned introductory chemistry, we learned like sodium chloride, potassium nitrate, lithium nitride. There's, tons of those names, and we don't really even think of what the system is going to be once we put that substance in water. You have to consider, though, that either of those ions is capable of interacting with water, and interacting with water capable of binding either hydrogen or hydroxide and leaving behind a hydronium ion or a hydroxide ion. So we have to start now considering the properties of an aqueous solution of a salt. And we think of it kind of like a tug-of-war. So the first type I want to talk about is neutral salt. Neutral salts are salts formed from the cation of a strong base and the anion of a strong acid. And the way I write that in my brain when I see this salt is I simply say, well, sodium as an anion making a base would be sodium hydroxide, and the chloride would make hydrochloric acid. These are both strong. In other words, these solutions in water, or these ions, are going to stay in ion form. Nothing's going to bind. And so what we would not have happen is sodium bind water to make hydroxide bound to sodium and making sodium hydroxide molecules or formula units, or the same thing with hydrochloric acid. Everything would just stay in ion form, and you would have lots of sodium ions in the system and lots of chloride ions in the system. And that's about it. No equilibrium would form, nothing else. So in this tug of war, neither of these ions is going to interact with water to change anything. So then we look at acid salts. Acidic salts are salts formed of the cation of a weak base and the anion of a strong acid. So if I have ammonium chloride, I would say my salt came from hydrochloric acid and ammonium hydroxide. And this is a strong acid. So when you put ammonium chloride in water, the chloride ions, they just fall into solution and stay in solution. Whereas the ammonium ions are going to interact with water chemically. Okay? So what we see happen is your chloride acts as a spectator, and then the ammonium hydrolyzes or splits water and creates an equilibrium system according to the Kb of ammonium. Okay? So this new system we have contains ammonium, water, splitting water into a strong acid ions and the weak-based ammonia, and that would be according again to the Kb for this ammonia. But if you notice, it's backwards. Our ammonia is over here, okay, as a product. So we would take the Kb for ammonia, and we could switch it using Kw for water into a Ka for the conjugate acid of ammonium, and we could then do some explorations into the mathematics of a particular system of a certain concentration of ammonium chloride. So that's acidic salts. Let's talk about basic salts. Basic salts are formed from the cation of a strong base and the anion of a weak acid. So sodium acetate is going to be our example here. This is going to form a basic solution when you drop it in water. We've played with sodium acetate before. It's what made the system that's supersaturated, that made the crystals really quickly. In this salt and water, sodium is a spectator, and the acetate ion interacts with water. In this case, acetate hydrolyzes water to form hydroxide, our strong base, or in this case, our strong base, and then acetic acid, a weak acid, intact molecule. And this equilibrium system formed according to the Ka for this weak acid. Again, the Ka is on the product side, so we would need to work with the Kb for its conjugate base. So that's the basics of those types of salts. Generally, we need to kind of understand that the pH of these salts are going to be even weaker than their weak acid and weak base counterparts. So if we have a basic salt, it's a little weaker than a weak base. If we have acidic salt, it's a little weaker than a weak acid. So when we're trying to determine the actual mathematic pH of a salt solution, we use the Ka of a weak acid formed to find the Kb of the conjugate base, or of the salt itself. We can then use the Kb of a weak base to find the Ka of the salt using this relationship. So when we have to find the pH of a salt system, we'll have the Ka or the Kb for the acid formed or the base formed So we'll see this equation get used in practice. This is on your College Board uh, um, resource sheets that you received for the AP exam. So nothing to memorize, just know it's available to you. When we speak generally about the strength, again, I mentioned this a moment ago, but basic salts are weaker than weak bases. Acidic salts are weaker than weak acids. And so as far as the pH goes, relatively speaking, this is the relationship you should consider. Now, could we make a basic salt solution more basic than a weak base? Sure, we can tinker with concentration until we get one stronger than a particular base. Yes, you can do that. But generally speaking, this should be the trend you would expect with a basic salt compared to a weak base and an acidic salt compared to a weak acid. So arrange the following 0.1 molar solutions in order of decreasing pH. That would mean start with the most basic substance, which should be sodium hydroxide. And there that is. And then next most basic would be a weak base, which on this list, you may still be getting used to the idea of seeing NH2 and knowing that this is very similar to ammonia, pardon me, and this is a weak base called methylamine. Then our next most basic substance would now be our basic salt. So what we're looking for is a salt that contains a salt of a strong base and a weak acid, and that would be sodium cyanide. And so we know that the sodium would go into this water solution and just act as a spectator, while the cyanide interacted with water to bind hydrogen to make the intact hydrocyanic acid molecule and then leave behind some hydroxide. Okay, and again, it's going to be according to the Ka for hydrocyanic acid, how that happens, and we'll show you that math here in a few minutes. The next most basic thing would be a neutral salt, like potassium chloride. Then following that, we would get into an acidic salt like ammonium nitrate. Playing animation, I don't know what that was for. And then a weak acid like phosphoric acid and a strong acid like hydrobromic. So hopefully that makes sense to you. If you need to fixate for a minute and go through it, please feel free to pause and do so. Okay, let's talk about the pH of a 0.1 molar sodium acetate solution. First and foremost, we go back to our rules of equilibrium. This is not a strong acid. Immediately you need to say to yourself, okay, I don't have a strong acid here. I've got to do some equilibrium examinations of what's going on. First of all, sodium acetate is the salt of a strong base and a weak acid, and so there's a basic solution going to be formed. We don't know how basic, but we can at least say to ourselves, expect a pH somewhere between like 7 and 10 maybe. So we'll just leave that up there for when we do the math here. We know that when this reaction takes place, this is what we see happening. We know the sodium falls into solution and doesn't do anything. We know the acetate will interact with water to hydrolyze it, form the intact acetic acid, and a little bit of hydroxide ion. And this is what's going to change the pH of our system to a basic pH. Next, what we want to do is we want to build our equilibrium. We started with 0.15 molar acetate ion. Again, it's a 1-to-1 ratio with acetate ion and the acetic acid. So we don't consider water because it's a liquid, and here our products of intact base or intact hydroxide and acetic acid are zeros. And so we pop through the equilibrium system to get our equilibrium expression, and then we're going to write a Kb. Okay, now the Kb is because we're producing hydroxide, but we're going to use the Ka for acetic acid, which for acetic acid is 1.8 times 10 to the negative fifth, which if you haven't gotten used to that number by now, it's a popular Ka and Kb. We can use the Ka for this expression, but we need to treat it as a Kb because we have the reaction reversed. Okay, so we use the ion product constant for water. Kw is equal to Ka times Kb to determine that value. So let's get on the next slide and do that. So the first thing we would do would be write our equilibrium expression, and this is our equilibrium expression with the acetic acid and hydroxide for products and the acetate ion as a reactant. We then have our rearranged Kw expression solved for Kb. Here's our Kw, here's our Ka for acetic acid, and we get a Kb value for the acetate ion. Okay, so this is going to act as a base, and it's going to accept a hydrogen ion to become the intact acetic acid. And this makes sense now that we have a Kb for it because it is acting as a base. So now that we have that Kb, we can plug our value into our equilibrium expression. We will neglect this x, and then we're going to solve for x. When we do that, we get a hydroxide ion concentration of 9.2 times 10 to the negative 6th. The question said, determine the pH, calculate the pH of the 0.15 molar system. So there's that. There's our concentration. And here's our pOH, 5.04. Don't freak out. That's a pOH. 14 subtracting 5.04 gives us a pH of 8.96. Is that within our expected range from the question start? 7 to 10? Yep. So let's go with that. That feels good. So again, you're checking the value at the end to determine if what you predicted is true to get an expected general pH or pOH. And in this case, it was great. So generally speaking, this is the way these salt questions go. You're going to get a value for a concentration of a salt. You're going to treat it like any other equilibrium system, but the reaction you have to write is the hydrolysis of water with that salt's ion that creates the weak acid or weak base system. Okay? Once you've written that hydrolysis reaction with water, you then write your equilibrium expression. You then take that acid or base that's created in the product's Ka value or Kb value and convert it to the opposite because your system's going the opposite way. You're using the conjugate base, in this case, to create your weak acid and hydroxide system. And once you solve for that, you can simply solve for your X value, or the hydroxide value in this case, and then convert that to a pH. So please go through that. Pause where you need to see what happened. Come to class with questions if you have them. Our final topic is acid and basic oxides. This is going to be a rare topic for AP, so this is a very low yield, but we want to bring it up. When metallic ionic oxides dissolve in water, they produce a metallic hydroxide. Let's be clear. Metallic oxide, calcium oxide. They make calcium hydroxide. When non-metallic oxides dissolve in water, they produce a weak acid. Non-metallic oxide, like carbon dioxide in water, makes carbonic acid, a weak acid. And then the final topic, I didn't mean that last one was the final topic, now did I? Salts of highly charged metal. Highly charged metal means something like aluminum. It's got a +3, highly charged metal. These tend to produce an acidic solution because of their attractiveness to water. So in an aqueous solution of aluminum chloride, we see this phenomenon happen where our aluminum water forms a little bit of hydroxide, or binds a little bit of water and hydroxide, splits water molecules, and makes a little bit of free hydrogen. So salts of highly charged metals tend to produce an acidic solution because they liberate hydrogen ions. And this is a model of what's going on. And you're looking at water molecules being attracted to water. And as they do so, you're getting a fairly strong bond between those water molecules and water. And the resultant impact is the higher the charge on the metal ion, the stronger the acidity of the hydrated ion. Electrons are pulled away from the hydroxide bond, or OH bond, and toward the positively charged metal cation. And you'll see a little bit of hydrogen ions be released from that system and create a slightly acidic system. Iron 3, aluminum +3. Solutions of iron 3 nitrates and chlorides tend to do this. Aluminum nitrates and chlorides tend to do this as well. So this is a little bit counterintuitive. You would expect, this is a little bit, this makes sense if you think about it. This is a salt of a strong acid and a weak base, right? If iron were to bind hydroxide, but really what we see is binding water and forming the hydrogen ions a little bit different way. Now the details in this are, I haven't seen a question on this in years, so this is kind of a topic that's rather fringe. But nevertheless, we wanted to bring this to you just so you can see that this is a phenomenon we see with highly charged metals. That's a slightly different than the expected salt of a weak acid, salt of a weak base we see. And that concludes the discussion on determining the pH of salt solutions.